Okay, so we have mentioned open cover compact, limit point compact, and sequential compact lastly. And how they imply each other. What's the two statement we proved last week? Which one imply which? Compact imply limit point compact. And then? Yes, good. Sequentially compact implies limit point compact. So for this two condition, right, it works with all topological space. Okay, all topological space. Okay. Hey, even before that, remember that how we prove compactness in Rn? Do you remember? Open book. Yes, it is closed and bounded. Hey, by the way, this guy is not in our class. Why is he answering faster than you guys? You should be careful. People want to take over you already. So we prove in Rn case compactness if and only if it is closed and bounded. How you think about this theorem? For example, in R, right, what things are compact? Closed interval, right? So closed interval is in particular, it is closed and bounded. Actually, there's a name for it. Okay, there's a name for it. We call this as a Hein-Borel theorem. Okay, so there's a name for it. So meaning closed and compact if and only if, sorry, closed and bounded if and only if it is compact in Rn. Okay, so yeah, so this one for Rn. Maybe use this color for Rn. Okay, so we will try and explore these conditions more. Remember what's the goal that we want to prove in the end? Last time we said, what's the slogan we had last time? We want to show that these three kind of compactness in metric space are equivalent. Okay, are equivalent. So this is what we're trying to achieve. Okay. We will fill in more in this mind map here. Okay, later we'll see what's the complete mind map we have. Right. Let's see what's the next thing we're gonna do. Sure. Okay, let's prove the first theorem of the day. We will prove that a metric space is limit point compact if and only if it is sequential compact. Sequential compact. Okay, so which direction we already have? Which direction we already have? Right to left. Okay, so it's the backward direction. So this is done. Okay. So what is left to do is we want to prove that if a metric space is limit point compact, then it is sequentially compact. Okay. Any idea you want to start? So if you want to prove sequentially compare, what do you need to do? Take a sequence and then show that it has a convergent subsequence. Okay. So given you a sequence here, how do you abstract a subsequence that converge? Given that it is limit point compact. So what's limit point compact? Means every infinite set has a limit point in your space. Every infinite set. So if you have a sequence, can you turn your sequence into a set or not? Can, right? So you just don't consider the ordering, correct or not? So is it possible that given you a sequence, this set is finite? Yes, right. How is it possible? Maybe you have some eventually constant sequence inside there. Okay, then they collapse to one element. So in this case here, can you extract a convergent subsequence or not? Yeah, because it is eventually constant, right? You just pick all the eventually constant term. It's a constant sequence. Constant sequence has a limit. So that constant sequence converges. Okay. But let's say, so let's write it down. So suppose Sn is a sequence in X. Okay. If the set of the sequence terms is finite, then we can extract a convergent, a constant subsequence, right? Subsequence. You know. Okay, so now, so in this case, now suppose this set is infinite. Okay, it's infinite. But if this set is infinite, what happened? By assumption. Sorry? This set here has what? Has a limit point. Good. So by assumption, A has a limit point. So it has a limit point, let's call it a name. Let's say little a. Okay. So what does this little a do? What does the limit point means? Every open neighborhood around A contains points in the set A, which is not equals to the little a here. Okay. So how do you extract subsequence here? Is it clear how to extract subsequence here? How to extract subsequence here? It tells you every ball, every open ball around this A contains points other than A. Then you choose a shrinking ball, right? Okay. But when you choose the shrinking ball, right, you will definitely choose a point from this Sn here, which is not A. But there's some technicality here, right? So for example, what's the technicality here? Let's say this point is A. Okay. If you pick B1, let's say this is B1, A. Okay, there's some point X1, maybe. Maybe X, say SJ1. But this XJ1 maybe also live in B half, let's say. Does it make sense? Okay. So how do you go around with this technicality? Maybe in B1, you already picked this SJ1. Then when you shrink your ball, this ball maybe contain SJ1. So how do you pick another guy inside this set here? Is there another guy for you to pick other than A and other than SJ1? Pick a smaller ball. That's one way to do that. That's one way to do that. Yeah, that's one way to do that. You can do it like that. Also can. You can do it like that. Um, then your radius is like irregular. You need to keep considering the distance between A and the newly elected point. And then you need to argue that that number have to converge to 0. Okay, that's one way. Is there any other way or not? Okay, you don't understand the technicality, so I'll repeat again. So let's say we start with a B1A, right? So we start with a ball first, B1A. I consider this open neighborhood, there's 1 point, right? By definition. There's points. I don't know how many points. There is 1. So I take this SJ1, correct or not? From this ball, there's not A. And then I consider, because just now we say we have to have a shrinking radius, right? So that the subsequence that we pick the distance with A is less than 1 over n. Right or not? So if we go to maybe half of it, maybe this guy are still there. Right?
The next ball, something like next ball.
Still contain it.
Yeah.
Sorry?
2 for 5
Sure. Yeah. If you want, you can go for his method, so you can skip this point. But my point is, in this shrinking ball here, I still can pick another guy other than A and SJ1. You know why? Actually, we prove that if a point is a limit point, right? That neighborhood should contain infinitely many points, not just few of them. Actually, infinitely many. So you can actually skip A, skip SJ1, pick another one. This is what we prove in the metric space chapter. Okay, if you are point in the, where is it? The closure. Is it closure or limit point? I can't remember. Do you remember what I want to claim here? Okay, maybe I recall for you. Wait, yeah, this one. If X is a limit point of A, then every open ball center that X contains an infinite number of points from A. Okay. Yeah. So there's a lot of choice you can make here. Is it okay? Hey, sorry, yeah. Yes.
Is 1y is smaller than the distance. So only find many xj and also find many all the n are not repeating. So why is that each?
Where is the issue? What's the issue?
Why is choosing the same point is each?
Oh, because it won't be a subsequence, right? It won't be a subsequence.
Oh,
You want it to be a subsequence. Subsequence you cannot repeat because subsequence is an increasing function. When you define subsequence, you cannot pick the same thing twice. The issue is the subsequence. Oh, this one come back to there's a story about this. This come back to this story here. There's one story. Actually, I want to thank when trying to pointing it out again. Remember that last time we showed this compactness. Where's this lecture 17? Remember that we show, what have we shown? Which lecture? Lecture, this one, yes. So when we prove that this closed set in a compact set is compact, right? Remember that last time we start with we want to show that A is compact, so we start with open cover of A. And then what we do is, we don't know about A, but we know about X. So what we do is we extend the cover of A to a cover of X. How do we extend it? We just add in the complement of A because we know that A is closed. So the complement of A confirm open. Okay. So it's an open cover of X. Then we use the compactness of X to reduce the number of these open cover to get a subcover. Okay. So last time, when Tran said that, can we just consider finite subcover here, okay, without throwing away this X minus A. But this X minus A might not be in the original cover, might not be. It could be, it might not be. Correct or not? It could be, it might not be. So you can't really just take F to cover the finite F cover to cover your A. Because if you just take F, you might contain something that's not coming from your original open cover of A. Then it is not a subcover of A. Okay. So seriously, you need to take away this complement first. Because it might not be in the cover that you started with. It might be in, might not be. Okay. Yeah. Thank you, Wenchuan, for pointing it out again. Okay. Actually, this how to say this criteria. I mean, not criteria. This how to say 这个什么啊？不是性格，还有一个字什么？这个啊，这个也不是条件，这个什么啊？当你形容一个人的怎样讲啊？这个特征、特性、特质，yes，特质。This character 啊，是叫 character 吗？英文，算吗？好像不准嘞。特质啊，
你算是啊，
我这算是，但是好像不太准确。就是特质啊，这种特质是你们都要有的，就是你们 study pure maths 一定要有这种特质，就是你可以回去 check 你自己啊，你不要以为全部 paper publish 全部都是对的，很长那种很出名的 paper 啊，都会重新 publish 一张东西叫做 errata。我什么叫 errata？就是它修改哦，里面有东西可能 proof 错，或者里面有一个 result 是错，它重新出一张 paper errata。明白吗？就算是 paper 啊，人家专业的人 check 啊，还是会有问题，明白吗？所以这个是一个你要学习的一个什么特征呀，素质呀，OK 了吗？很重要啊，你要自己 check 你自己，一直 check 你自己，这很重要，这个很重要。OK，where are we just now? Okay, so I mean, from today onwards, until we finish completeness, maybe sometimes my proof is not how to say. I don't want to write down every single word. I think quite consuming, and then also I think you at some extent you see similar proof already. Okay, not just from this class, actually from your MA, I guess. Yeah, you should have seen it. But I will include the full proof inside my lecture note. Please read. I urge you. I plead you, please read. OK，不要什么用自己的感觉啊，用什么自己的什么想法，不要，千万不要。OK，监督一下人家怎么去理解那个事情。OK 吗？Make sense? OK, please read. All right. Everyone okay with our searching for subsequence? I don't want to write all the steps. Very technical. Please read the notes. Okay or not? Do everyone get the idea? Okay. Okay. So short word is there's infinitely many points inside your open neighborhood, so you can avoid all the previous choice you made. That's all. Okay. And then because by the construction of this shrinking ball, the distance is getting closer and closer to your limit. Okay, so there's a subsequence that converge. Okay. Okay, good. Let's continue. So I will define a very useful property which is called the totally bounded. Okay, a subset of a metric space is totally bounded if for all epsilon greater than 0, I can just cover this A using finitely many balls. Hey, you see this definition here quite similar to compactness, right? Quite similar, right? So what's the difference? What's the difference with compactness? Yes, for compactness, you start with any open cover and then you can reduce it. But here, we just say that this A, you can use enough, just finitely many balls to bound it. Okay, there's the difference here. Okay, so for compactness, you need to check for every open cover, and then you can reduce. Okay, but here, we just ask whether this set here can be covered by finitely many balls or not. Okay, good. Thank you. So epsilon should appear in the phrase here. Is it? Yes. Okay, so actually it is asking that you can use any radius of ball to cover it, and then you just need every time you just need finitely many of them. Maybe the number increase, that's fine, but as long as it is finitely many of them, that's okay. Okay, any ball, hey, this any ball is quite strong, you know. Remember when you see epsilon, what you should think? You should think about small number. So even very small number, you just only need finitely many of them to cover it. So we call it totally bounded, quite strong. Okay, quite strong, totally bounded. Does it make sense? Okay. Okay. Right. So let's prove some property. How about how do you relate totally bounded and bounded? What do you think? Which one imply which? Yeah, I mean from the English point of view, should be totally bounded implies bounded. Because since we already add an adjective to this bounded. Okay, so we try and prove it. So how should you think about this? How to prove something is bounded? Remember? Bounded definition again. And what does n do? Okay, sure, you can take is it true for OM or there exists an M? There exists an M. Check. I feel like if there exists an M that's true for all X. You can center your X at everywhere, center your ball at everywhere, but using the same radius. Is it? Check. Anyone can check or not? But what's the definition? The original definition. I think I remember that one is the proposition, right? If and only if equivalent statement. Yes, there exists an M that can bound any distance of any 2 points. Okay, that's the original definition. Hey, anyone found the ball definition or not? Anyone found the ball definition? Is it true that there exists an M that's such that for all X, your set is living in the ball of radius M centered at X? Is it? Very important, if you switch the quantifier, then something is it. For all center, there exists an M. So this M can change on. Okay, depend on your center. Okay, it's enough. If there exists an M for all X, that one is stronger. Okay. All right. So how to prove this? Any idea how to prove this? So we want to show that there exists an M such that dxy is less than M for all xy. How about I give you 2 minutes? Try see what M you can take. What M you can take? Let me write down the assumption we have first. Yeah, see what M you can take. So how should you think about totally bounded? What's the image in your mind? If I have a set, if it's totally bounded, that means I can use finitely many ball to cover it. Okay, so you should think about this. Something like that. Okay. And then now you want to show that any 2 points, okay, the distance here is less than some M, 6M, or chosen M. Any 2 points. Okay, so what we can do here, we can choose x1 to xn in X such that we use radius 1 ball, okay, to cover our space. Okay, there are finitely many radius 1 ball that can cover our space X. See? Okay, so what's the M here? If you want to compute, sorry, let's do it here. So for every xy in X, how do you compute dxy? Can you link dxy to one of these ball or not? Can, right? Okay, so I mean, we can say link it to some dx xi. I don't know what I, but some I like this. Okay. So what? Is this enough or not? Is this enough? Maybe when we do this, what are we aiming here? What is this I doing? So say, so I mean these are working. So let's make it another color green. So X maybe is inside B1 Xi, like that. And then same. Is it always true that Y is in the same ball or not? Maybe not, right? Then we need to do something else, right? So we try to be as general as possible. So maybe Y is living in some other J not equal to I. Maybe equal, maybe not equal. So why I want to make sure they live in the same ball first? Because we have the control on the distance of point inside the ball. Okay, so maybe we do this. Okay, so for all these, which one we have control? The first one, the last one. Okay, control by 1. How about the middle one? Can we control or not? How do we control it? Yes, we only have finitely many of the center of the ball. So we can consider the maximum. Okay, we can consider the maximum of the set of all the xi. So I can just set this as my m. Okay, my m is 2 plus the maximum of the distance between two center. Okay, this is my m. Okay or not? Make sense? Make sense or not? Okay. All of these are constant now. One constant. This one also constant. Achievable. Okay. Agree? Okay. Yeah. Okay, good. Right. So is the other direction true or not? Is the bounded set totally bounded? Yes or no? Okay, guess with your intuition. No. Okay, because I didn't prove it. Okay, I mean, right. So give you example, a bounded space that is not totally bounded. So bounded space means every 2 point, your distance is bounded by a fixed number. Not totally bounded meaning you cannot cover every point using finitely many balls. Okay, can you think of this kind of space or not? The distance is bounded, but you cannot cover them using finitely many balls. Wait, okay, good. Wait, let me write down first. Okay, one by one. Okay, like Z square, like this. Like this.
Yeah.
Okay, and then
So every point has or no,
not quite bounded, right?
maybe a close
Closed subset.
yeah.
Closed subset. And then is it totally bounded? But you already close subset of Z. I think Z already finite already, right? Your Z is finite, is it? If you want to take a subset, closed subset of Z. Is your set finite or not, first of all? If it's finite, then should be totally bounded already. I don't know. So in order to like give this kind of counterexample, you should start with an infinite set. Like try R with discrete matrix. Okay, with discrete matrix. So is it clearly bounded? Clearly bounded, right? 0 or 1 only. Okay, is it totally not totally bounded? Yes, good. So if you choose epsilon to be 1/2 of x, such that x is in R, this has no finite. Can I write like this? Has no finite. How to say? How to write it now? I just say no finite sub cover. Is it clear or not? Cannot cover it finite. So you cannot, how to say? Use finitely many of these balls to cover your arm. So finite subcover. Huh? Not totally bounded by this. I think this one a bit weird. Not totally bounded by this. Because totally bounded have to work for all epsilon. So I mean, yeah, I just want to say this has no sub. I think it's enough to imply. Is it enough? Right. There's no finite set from this guy to cover your arm. Okay. Is this true or not? I think it's true. Yeah. Because what happened is you push every point one distance away. One distance away. You push your point one distance away. If you are not me, then you are 1 meter from me. You are not me, 1 meter from me. Okay. Discrete metric. Okay. Yeah. But the distance still only 1 meter away. Okay. Okay, but we are going to prove that if you are the subset of Rn, then totally bounded implies bounded, and bounded implies totally bounded. This happened in Rn. Okay, these two things is true in Rn. So here Rn are very important. Here Rn come with a Euclidean metric. Okay, just now we play a trick. We change the metric. Okay, here is the usual Euclidean metric. So should we put here in Euclidean metric? Okay, so this is the trick we play. Same space, we change metric. Same set. Okay, I don't want to use space. Space a bit general in our course. Use set. Same set of element, different metric. Okay, so it become different metric space. All right. To prove this, okay, maybe we just go through what we have to go through first. I give you a live experience of this proof. Okay, I will show you what's live experience. I don't want to do the usual lemma proposition. I will let you see why we need lemma. Okay. So which direction is clear? Yes, so the forward direction should be clear already because we already proved it for general metric space. This one is just one of them. And so it should apply. How about the other direction? Okay, the other direction, suppose x is bounded. We want to show that it is totally bounded. Okay. So how to show it is totally bounded? We need to, for every epsilon, we want to find what? Finite cover. finite ball to cover it. Okay. Can we do that or not? We only know that X is bounded. Can we do that? How? I give us an outline. You say yes, man? Give us an outline. Why laugh? Nothing to laugh at. Serious. We are discussing seriously. So what's does yeah? Or you want to use the showing that the Cartesian product of compact set is compact? Can you use that? That kind of idea. How it works? Why it works?
I get this thing is here.
I mean, I also think it will totally bounded lah. But we need to prove lah. This is the point lah. We need to prove. The point is we want to prove. So Y is enough to have finitely many ball to cover the X, finitely many ball to cover the Y. This is what you need to answer. You get what I mean? Okay. So if it's bounded, what does it mean? This set here should be contained in some, not just ball, I want to contain it in a cube or rectangle. Okay. Can you see why I want to bound it using a cube or not? Sorry. This set is what? Cartesian product of compact set. So this guy is compact. Okay, this guy is compact. Yeah, this guy is compact. But we want to show that X is bounded, totally bounded. Is this guy totally bounded? Is this guy totally bounded? How? What do you mean? So I give you any random radius, right? Okay, you need to argue for me. Okay, why only finitely many of this ball needed? But from here, at least from here, can you see that you only need finitely many of them? You can divide, right? Correct or not? But the point here is you are a mathematician. You need to tell me how to divide. Okay. Sorry? K over epsilon, is it enough? 2 epsilon. Okay, maybe I'll write down the estimate here. So what's the estimate here? Let me write it down. So first we are given epsilon first, right? Okay. Then how do we set our open ball? So let's define this open ball here. So open ball, the main point here is you need to give me your center and give me your radius. So this is the two things you need to decide. Okay. So let's call it B epsilon of center. You already know it decide already. I already tell you I want an epsilon ball. Okay, you don't need to decide. So you need to decide what's the center now. Okay, so what point you need to place so that you can cover everything inside your rectangle. So how do you decide this? Yes, you need to divide. Okay, but how do you divide it? So how do we pick this center in particular? So let's fix our center point first. And then how we pick the center is we go and look for the integral point, meaning the integer how to say, integer point, the point that every coordinate is an integer, because you are a cube inside Rn, right? So definitely you will cover some integer point. Make sense or not? Does it make sense? Does it make sense? So you are living in R3, right? I mean Rn, sorry. In this case here, we draw it as R3. And then definitely you have this integral point inside your cube. Correct or not? Maybe your cube too small, huh? The radius is 1/2. Wait, you see here. Our t here is chosen as in this format, minus kk. Okay, so we will try and argue. We could try and argue why this integer point can cover the ball. So how do we choose this integer point at first? So we need to make sure that the length of each ji is less than equals to 2k over epsilon. 2k over epsilon. Should it be strictly less? Strictly less, let me think. So the claim is this one should cover t. Let's think whether this cover t or not. Okay. So 2k is what? 2k is the whole interval, right? From minus k to k, the distance is 2k. Okay. And then epsilon is the distance that you can cover. Okay. And is this enough or not to cover t? So what we want to argue is t live in the union of this ball. So t is one of the point inside one of the ball. Okay, every point in t is one of the point inside one of the ball. Okay, this is what we need to argue. Is that true? Is this true? Is this true? Maybe we use a smaller example to think about. How about we use R to think about? Maybe we use R like this. Okay, and then let's pick a subset interval. Maybe maybe what interval you want? Maybe -3 to 3 like that. Okay, and then what epsilon you want to pick? Just now you said small epsilon might be got problem, right? So let's pick small epsilon now. Sorry, half. Small enough. Okay, let's check half epsilon. So in this case, what's the j we are considering here? So here we have distance here is 6. So 6 divided by 12 by half, we should get 12. So we need 12 ball. Okay. And then what? And then what are the integral points here? So we have integral points, maybe 1, -2, and then 1, 2 here. Okay. So how do we place this half ball? How do we place this half ball here? The claim here is want to pick at the integer point. So at least we need to put it at here, 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 here. Is it? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 only. There's some point we haven't covered yet, right? So how happen? How to do? What to do here? Any idea what to do? How to fill in this blank? It's blank. Sorry? Oh, cannot extend. Radius fixed already. I say I want half radius ball. So the thing you can do is you can add ball. But how do you add ball? No. This is our one of our how to say method. So seems like still lack of something. We need to add in. What should we add? How can we modify these open? There's another issue. I mean we can make this strictly less. Is it better or not? I don't know. I mean the answer wouldn't change much. Just it is about technicality. So you need to how to deal with the boundary like that. Okay. But I mean we just fix one of them and then see how it goes. Okay. So what do you think? What do you think? How to act? How to cover the rest? I mean, obviously from here, there's only finitely many you need to do, right? Just that how you introduce your open ball now. Okay, just now I said that we can pick the integral point and then put the ball there. Yes, and seems like maybe you might miss some of the points. So how should you add more ball into it? So you see, if I cover half here, what's the point that I miss? Only missing it's not intersection, but okay, intersection of their boundary. This one makes sense, right? Intersection of their boundary. Yeah. So what ball is this? I mean, yeah, intersection of boundary. Intersection of boundary. I mean, okay, if let's say we make it worse, make things worse. So make things worse, I make this smaller a bit, even smaller. You wanted. I not make things worse. Okay, so then the thing that they don't cover is what? The middle wanted, yes. A bit like a Cantor set like that. Middle wanted. Okay. Middle wanted. No, right, because radius is wanted. It's not diameter wanted. Yes. But if we want to add ball in the middle, does this idea extend to Rn or not? Is there a middle inside there or not? How do you take the middle or the midpoint that you want to that you miss? Okay. Can the idea extend to Rn or not? I feel like this construction should work. Maybe I missed out some condition here. There should be some more condition, I guess. This one. Yeah. Any idea? If not, then maybe we'll resume talking about this next time. I leave you go back and do, and then I also do. Oh, got idea now? Yeah. Okay. I think I get what this grid means already. Is actually this is not Z actually. Okay, I think I get the. I mean, I understand the maybe the argument wrong. It says integral lattice. Maybe it's not just integer. Okay, integer. The integral lattice for Z, the distance is 1. But now we make the grid to distance this thing. You get what I mean? So let's say, okay, I think I now understand what the book says. Okay. So for example, just now, if I want to smile in this case here, okay, instead of looking at the integral lattice of Z, right, we should look at the integral lattice of, let's say, 1/3. So we need to split every, how to say, split this number line into 1/3, 1/3 like that. Okay, and then I consider the 1/3 ball. So where is the 1/3 ball? 1/3 ball like this, or like this, or like that. So this 1/3 ball should cover how many lattice points? To cover, let me think, 6. I mean, if it's not covering the boundary, it should be 5, right? Okay, let me draw it to you. What is the 1/3 ball here? What's the 1/3 ball here? So 1/3 ball should be like this, center at -3, and then 1/3 ball at -2 like this. So at every integral point, you pick this. Does it make sense? Is it too big? Oh, sorry, too big, huh? So 1/3 should be like this, Okay, like this. Okay, like this. Okay or not? Yeah, so I understand this wrong. So this shouldn't be just a integer lattice. This is the integral lattice with distance 2k over epsilon. Yeah, then this one makes sense. Okay or not? Does it make sense? Can you understand what we are doing here? Can you understand, everyone? So I have 3. So I have a -3 to 3. If I want to cover it, cover with 1/3 ball, then I split the distance into 1/3, 1/3, 1/3, 1/3, 1/3, 1/3. Okay. And then at every integral point, so at every these integral point, I make a 1/3 ball. So you can see that if I make this 1/3 ball here, okay, maybe I use a different color. They will overlap. So here 1/3 ball, here 1/3 ball. At every integral, at this point. Okay, make sense? Okay. Okay. Okay, but still, what we have shown is this T is totally bounded. What we want to show is X is totally bounded. Okay, but you can show that any subspace of a totally bounded is actually totally bounded. Okay, you can do that. You want to try yourself or you want to discuss a bit? So T is totally bounded. So you can prove a lemma. Lemma is any subspace of totally bounded space is totally bounded. Okay, it's totally bounded. Is it hard to imagine or not? Okay, everyone okay? Yeah, try and prove this. I've included some picture inside the lecture note, which you can see later. Okay, yeah. So any questions so far up to here? Any questions so far? We have proved that in Rn, every subset is totally bounded if only if it is bounded. Okay. If not, like maybe we take a break until 1:15. Okay, then we will resume. By the way, we set the presentation time at next Tuesday, 7 to 9. So even though most of you are not presenting, if you want to come and listen, you're welcome. You can come. We are at A5. Your friend don't want you to come. A5, A5 where? G01. I think it's A5 G01. Lecture hall, yeah. A5 G01. Yeah. So when Chan will talk about topology with p-edit integers. So you want to prove that p-edit number integers is a complete metric space. Yeah, one of the results. So you might wonder what's the distance, something like that. Other than that, you might think there's only one presentation. Why there's 2 hours? Because I have a MA1 presentation also. So all of them have to do presentation. They will speak about MA theory, like for example, Bolzano-Weierstrass, like that. And then I want them to discuss from the viewpoint of that mathematician. So for example, why Bolzano will come up with this theorem or how they prove it, something like that. Okay, so understand through history, okay, how this mathematics get created. Okay, so they will discuss the mathematician and also the theory they create. Okay, yeah. So my topic for them is I'm a mathematician. MA 有做那个什么Auxiliary exponential theorem，有没有讨论 equal continuity？我们不是有讨论 completeness？没有啊，没有 completeness？没有哦，有啊，应该有啊，应该有吧
Completeness is what? Completeness excellence.
不是 complete excellence，complete metric space。
Metric space.
你又知道没有？你读过没？你在这边打过课了没？打过 MA 完了。哦，你拿 MA1 啊 ，MA1 应该是没有啦，把 MA 这个啊，对，他没有讲 metric， 但是他应该可以直接讲那个 Cauchy sequence 是有 limit 吗 ？Then 他就 complete 咯 ，then 他就可以做 equal continuity 的东西。
哦，从那个Cauchy
有还是没有啊？有什么 equal continuity 我是说有没有做到？有印象？ 不可能 equality 应该只有一种吧 equality 没有别的名字。compact 还有可能不一样一点，可能他用 sequential compact 啊什么这样。equality 应该是只有一个名字吧。EQI。以前我们没有 prove 啦，但是我们有讲过。没有啊 ，not 里面也没有，也没有。可是我记得它的 not 里面有写 Ascoli， 哦，可能是 Topology 里面哦。
那个是 Topology，
因为以前我们做的时候，我们也是只做在 Matrix Space 吧。Matrix Space 就可以讲一个 version 出来了。要 reconnect ，so I mean for this compactness, right? We will stop at completeness first, okay, and then we'll talk about countability. So meaning, if you have a basis, how many bases you need? Okay, if there's only countable many bases you need, it's countable. A space is countable. And then we'll talk about separability. So actually, you have met separability already. You have met hot space, and then we introduce the T1 space. Every one point set is closed. Okay, and then later we will do more, so like T3, T2, T4, all sort of T. Very crazy one. Topology is quite crazy. Anyway, but at least not too useful for my research now. But I mean, we just explore. So I mean, about this T thingy, you can talk about factorizable, what space you can put distance again between 2 points. Okay, you can put matrix between 2 points. When can you do that? Okay, depends on how you can separate your wall. I mean, separate your points inside of set. Okay, how separable is your space. And then you can, through separable, you can talk about compactness as well. Or countability, you can talk about compactness as well. And then after this final exam, or not yet. Okay, before final exam, we will, I think I want to talk about the Escola solution. Maybe we won't put too much, I mean, exam assessment on that thing, but I think I want to talk about that. I think that result is quite important result for matrix space for things like that. A solution. Where we will, I think we have to spend time talking about. But we won't assess it. That theorem is quite involved. But we want to talk about this. Okay? Yeah. Actually, we are finishing soon already. So you already go to the Malay, we say kombucha. English is pig. Yes, pig. I don't understand talk about as a pig. Actually, you already passed by the pig. So last time you feel very stressed is very true because actually that's the pig. Okay, after that pig, then you feel so already. It's like how they first time learn, like the student first time learn MA1, also like that. You reach that peak, and then MA2 is also epsilon delta, maybe just more dimension. That's all. Yeah. So human is like that. After you meet a peak, and then after that peak, and then you'll feel better. After you're feeling better, you'll meet another peak. Another peak. So the problem is how you deal with this peak. If you deal it well, then it becomes a strength of yours. If you do it bad, then maybe it becomes your bad memory. Yeah. So every peak is your challenge. Okay, you need to do it well. Okay? It's your challenge. After this peak, then it becomes your experience. Right? It becomes your experience. All right. Sure. So there's a lemma that I feel like I don't want to prove it. We have do too many technical stuff in this class. Delay the time already. I will put it into my lecture notes. I even draw some nice picture for you to see. So you can deduce the Lebesgue number. Last time we deduced it using open cover. Actually, you can deduce it using sequential compact. Okay? You can deduce the Lebesgue number lemma using sequentially compact. Okay. I don't think I want to prove this in this class now. I will put it in the lecture notes. Please read. Please read. I made a picture for you to refer how does this proof work. Okay. Basically, this lemma is this proof is a bit different to what we had last time. Last time we are quite constructive, right? This proof is using a contradiction. So why do I want this lemma here? So finally, we reached our goal that we want to prove that in a metric space, all three stuff is equivalent. Okay. All three kind of compactness is the same. Is the same. Actually, there's only one direction we left to prove, you know. Which direction? Let's see. Let's go back to our MindMap for a while. We have shown that compact implies limit point compact. Sequential compact implies limit point compact. And just now we did a direction that going from limit point compact to sequential compact. Only in metric space. Not metric space. So to go around these three things, right? What more arrow you need? Huh? I can go from here to here already. Here to here. Sequential compact to compact. If we have this triangle, can we go around? Cannot? Okay. So we left with this. Okay, either you can do this lah. Either I think you also can do this. Okay, but we will choose to do this. Sequential compact to compact. Okay, let's try do sequential compact to compact. Prove sequential compact to compact. So suppose X is sequential compact. We want to show that it is compact. So what do we need to do? Take any open cover. We want to find as a finite subcover. Okay. So also suppose that C is an open cover of X. What else we prove? Let's see. I think we missed something. We missed something. We are missing something. We need to go back a bit. We're missing something. So we have this Lebesgue number. We should also have another lemma to be useful. I introduced totally bounded. I haven't used it yet, actually. I just showed that totally bounded is bounded. And then in Rn, totally bounded implies bounded. So actually, we want to show that every sequentially compact metric space is totally bounded. I think it's good to prove this, I guess. So let's prove this. Okay, let's prove this. So how to prove this? You don't have much condition on the space, right? You just know that it is sequentially compact. Just says that every sequence has a convergent subsequence. But how to say that there's you need only finitely many balls to cover it? You want to cover sequence, but you still need to cover the whole space. So do you want to come? Yeah. So how to go around with it? So the best way is use contradiction. Okay. So suppose so let's say this space is called X. Let's say suppose X is not totally bounded. Okay? Because if you suppose it is not totally bounded, you have something to work with. What's the thing you can work? That means there exists a epsilon such that the ball of epsilon of X in all the point in X, this guy has no finite subcover of X. Okay, so you have some ball to work with now. Okay. So from this ball, can you construct some sequence that doesn't have a convergent subsequence on it? Yeah. Yeah. So can you construct a sequence that doesn't have a convergent subsequence? So you need to tell me what is S1, S2, Sn, so on, right? Got any idea? So you just simply take any point in X first, right? And then okay, good. So I don't want it to be very close to my first point. Okay, what can I do next? Okay, so I don't want it to be too close to both of this point. Stay far away from these 2 points. Okay, and then you can keep going. Okay, keep going because you have infinitely many ball that how to say to play with, right? So we define xn to be x. So to be the complement of the union of all the ball centered at xi defined inductively with radius epsilon that this I is from 1 to n-1. Okay. Is this possible or not? You need to argue, is this possible or not? Is this possible? Can we always pick a point out from this complement or not? Can we always do that? Why? It's already x. Okay, if not, that union of ball is already x. So it must be always non-empty. Because you need to keep covering. Does it make sense? If empty, if this thing empty, then equal already. Right now. Cannot be empty one because you don't have finite subcover. So we can always do that. Okay, we make a sequence. Then the final thing you need to show that it doesn't have a convergent subsequence. Okay, how to show that? Suppose it has no. Okay, if xn has a subsequence that converge to a point A. Okay, what happened? Then the d of the two large number jk, it is less than or equals to dxj a plus da xk. Okay, maybe you can pick it because converge, right? You can pick it less than epsilon over 2 for both. Then you will make sure that sj and sk is within epsilon. But every time we pick this xi, sj, they are at least epsilon away. Okay. Okay, so this ball is very good separating these Fj that we pick. So contradicting the choice of J. Okay. Because we pick them at least epsilon away. Okay, good. So I think it's good that if we add some property here. So in metric space, sequential compact implies totally bounded. And in the random metric space or topological space, yeah. Metric space, totally bounded implies bounded. Okay, let's use ping for metric space. But in Rn, you can work the other way around. Okay, you can go down from bounded to totally bounded like this. So this is the relationship between these two. So far, we have established. But we want to prove this one. Okay, not yet established. Okay, so far okay. Okay. Okay, good. Let's go down. So how good is this? So we want to show what? What do we want to show? We want to show compactness, right? We want to show compactness. So how are we gonna use these totally bounded property here? Okay. Right. So what do we do? What does Lebesgue number lemma do? What's the statement for Lebesgue number lemma? Can someone tell us? If I give you a open covering, what happened? Lebesgue number lemma is compact. Right. If compact, then this delta exists. So what does this delta do? Then there exists an element from your open cover contain it. Okay. Yeah. So meaning there's a delta such that that ball will live in some of the element of your open covering. Okay. Okay. So I mean we are sequentially compact, right? Okay. It also implies this Lebesgue number theorem lemma. So by Lebesgue number lemma, what we have is there is a delta greater than 0 such that for every point in your space, okay, the ball delta around X is in some of the element inside your open cover. Okay. So you are covered by some element inside your open cover. Okay. But what? But your S is totally bounded. Okay, we show that every sequential compact space is totally bounded. So what happened to this totally bounded space? Every open cover by a epsilon ball, you just need how many of them for totally bounded set? How many epsilon ball you need? Finitely many. Okay, so the open cover, by these Lebesgue radius, Lebesgue number radius of ball, you just need finitely many of them. Okay, this cover here has a finite subcover, meaning you just need finitely many of radius and form this delta ball. Sorry, this is delta. Okay, you just need finitely many of them. Okay, so your finitely many of ball already cover your space S. And your open covering have an element that cover your ball. So how do you pick your finitely many U here? So for every I equals to 1 to n, you just simply pick ui in your cover such that your ui will contain these finitely many ball individually. Okay, then you only need infinitely many ui. Okay, so now since the union of b delta of xi cover x, right? Surely this ui also cover your x. Okay. Does it make sense? Does it make sense? X. Okay. So we use the Lebesgue number to make a radius of Lebesgue number ball to cover our space. And then because it is totally bounded, we only need finitely many of them. But this space is what? This space is okay by Lebesgue number lemma. What can you talk about this ball here? Ball of radius delta. There's some element in your open cover that cover it. Okay. So you already use finitely many ball of radius Lebesgue number to cover your space, and surely you just take finitely many element from your open cover to cover your whole space. Yes.
The delta is for the open covering for the open ball.
Open ball. But this open ball is special. It is contained in some element inside the open covering. So this delta is given by your open covering. It's decided by your open covering. You start with an open covering that exists a delta. Okay. So this delta depends on your open covering. If you give me different open covering, maybe I need different delta that works. But anyhow, totally bounded says what? For every delta, you just need finitely many of them. Okay or not? Yeah. Okay. Is it clear? Okay. Are we good for this one? Yeah. Okay. So if it's good, we will introduce completeness now. So hopefully we get very good result today. So what is the Cauchy sequence? I think you do assignment already before we introduce this. What is the Cauchy sequence in a metric space? It's really the same as the case in R or Rn. What's the Cauchy sequence? If what? For every epsilon greater than 0, there exists an n in n such that, maybe I use capital N, such that for all jk greater than capital N, okay, any two terms behind capital N, the distance between xj and sk is less than epsilon. Okay. Not that this is not just consecutive. This is like everything behind to squish within epsilon. Everything behind n cut off need to squish. If you just consecutive, maybe still diverge, or like for example, there's a graph called square root x. Square root x diverge. Although you see like it is getting like how to say less increasing, can I say like that? Yeah. But it's still diverge. But you can see that some kind of asymptotic curve, right, also increase like that. But they somehow converge to an asymptote. So this is the thing about this Cauchiness. You cannot just getting closer to each other consecutively. you need to get closer altogether. Every two terms behind, and you have to get absolute close. Okay, then it is Cauchy. Then I can confirm you that it is convergent. But this convergent is a bit special. If the limit doesn't exist in the space, we won't say it is convergent. Okay, but in R it is because R always, if you converge, you should have a limit there because it's complete. So that's why we split out the idea of completeness now. Okay, because if you consider a sequence in Q, the limit might not be in Q. Maybe you converge to pi, converge to irrational number. Okay, so the theorem here is every convergent sequence in a metric space is Cauchy. Okay, is Cauchy. Is the other direction true or not? Not true. If it is true, then we will say that this space is complete. Okay, if the other direction is true, then we'll say that this space is complete. Okay. For example, Q is not complete. Okay, but R is complete. Okay. So the metric space X is complete if every Cauchy sequence in X converges to a point in X. Okay, if the other direction is true, then your space is complete. Okay, so if you want example, maybe Q is not complete, R is complete. Okay, I think we won't prove this theorem. You can try and prove it. Try and recall your knowledge. What sort of interesting result here? One thing about completeness of R is you remember the completeness axiom. What's the completeness axiom you've been introduced? Is it the least upper bound axiom? Least upper bound axiom. So every non-empty subset of R bounded above has a least upper bound. Okay. So this is how you build irrational number. Right or not? How to argue there's a square root 2 as this? You argue that S squared less than or equal to 2. Less than 2 has a least upper bound. Yeah. Okay. Then we call that number square root 2. Okay. And the other way you can do it is you consider the irrational number as the limit of Cauchy sequence. Okay. So you can put in the conditions that every Cauchy sequence converges. Then you can build your real number. Because so in that case, your real number becomes what? Your real number becomes a bunch of equivalent classes of Cauchy sequence. Yeah, your real number becomes equivalent class of Cauchy sequence. Because maybe you can take two different sequences that converge to the same value, right? Okay, so in that case, your real number is not just a number, it's a sequence already. It's not just sequence, but equivalent classes of sequence. Okay, if they have the same limit, you treat them as the same number. Okay, and then not enough, not enough. For this criteria, you still need the Archimedean property of R. Okay, so that you can imply the least upper bound property. So what I want to say here is there's a very good theorem, but we won't prove it. That's just what I want to mention it out. So I want to say that in R, least upper bound axiom is equivalent to convergence of Cauchy sequence plus Archimedean property. Okay. We won't pursue this proof here. I think not even in my lecture notes, but I will refer you to the right references. The proof of this is just MA1 knowledge, MA1 type of proof. You play around with this sequence, epsilon, delta, this thing. Okay, yeah. But I think this is a very important theorem that you need to know to prove that you really learn mathematics. Otherwise, you're not learning mathematics. This is the basic thing we build real number. Okay, this is how we build real numbers. We have 10 minutes. Okay, quick. So, before we going to this compactness if and only if complete and totally bounded, let's prove one more theorem. Should we prove now or prove later? Let me see. How about we prove this completeness if and only if closed later? Wait, let me check. Do I need this or not? Okay. How about we go to the main duty here? Let's see if we need that or not. So let's go to the main dish today. A metric space X is compact. So last time in Rn, we know that it is closed and bounded, right? Now we want to push it to random metric space. Okay, in Rn, what happened? Rn is completed. Okay, so you need closed and bounded only. But in general metric space, no completeness for you already. Okay, so if you want to be compact, you have to be complete, not just bounded, but actually totally bounded. Okay, very strong, quite strong. Okay, let's prove this. So one direction. So let's do the forward proof first. So now suppose X is compact. Good. X is compact. This is metric space, right? Okay. So in particular, X is sequentially compact. But what we have proven here, sequentially compact implies totally bounded. Okay, this is what we have proven just now. So we are left to prove completeness. Okay, we are left to prove completeness. So to prove completeness, what's the definition? Every Cauchy sequence must converge. So let's take one Cauchy sequence now. Suppose Xn is Cauchy. Okay. Suppose Sn is Cauchy. Hey, this thing is sequentially compact. What does it mean? What happened to this Cauchy sequence? Huh? Not yet. Limit point of who? Whose limit point? Sequentially compact says what? Yes, subsequence. Only subsequence for now. Then this Xn must has a convergent subsequence. Okay. Let's say it converge to some number, say L, for example. Where converge to L? But what can you prove? A Cauchy sequence with a convergent subsequence must also converge and converge to the same limit, okay, which is L. Okay. So actually, it's a similar, I guess, similar proof in MA1. You will show that a Cauchy sequence with a convergent subsequence also converges to L. Okay, if you want to recall, I suggest you to write down the proof of this. Okay, I suggest you to write down the proof of this. Okay, but the takeaway here is a Cauchy sequence with a convergent subsequence also converge. and then converge to the same limit. Okay, so hence our space is complete. Good. Yeah, our space is complete now. How about the other direction? Conversely, what happened? Suppose X is complete and totally bounded. We want to show that X is compact. Okay. So the way I did here is we use sequentially compact. Okay, so we show that. So our goal here is to show that X is sequentially compact because it's equivalent to compactness, any compactness you want to use. Okay, let's say we want to show that it is sequentially compact means what? I need to start with random sequence and then show that it has a convergent subsequence. Good. So what do we do here? So let's say we just start with a random sequence. Let's call it Sn. Be a sequence from X. Let's denote it as Sn1. Okay, let's denote Sn by Sn1 because later we want to build subsequent out of this sequence here. Denote this sequence by the first one, the first sequence we look at. Okay. So how do we build this? How do we build subsequence here? How to build subsequence? What's the condition you have here? Completeness and totally bounded. Completeness, what do you think we need completeness for? What do you think? What does completeness give you, for example? It gives you a limit, right? Okay, so maybe later when converge, we need this limit property. Totally bounded tells you how far the point to each other. Okay, how far the point to each other. Okay, so we're gonna use totally bounded to pick our subsequence here. Okay, let's see how we pick this. So first, we want to find a convergent sequence, right? This totally bounded have one nice advantage, right? It works for all epsilon. So we also try to use shrinking ball radius to pick subsequence. Okay, around the same technique, you would say. Okay, across these proof. So using 3 minutes. So using totally boundedness of X. Okay. First, we cover X by radius 1 ball. Okay, finite number of radius 1 ball. What do we observe actually here? What happened to my sequence and this ball here? What's the interaction between these two? You have sequence, and then you have finitely many radius 1 ball. What's the interaction between this ball and this sequence? Remember, this ball contains every point in my space. In particular, some of these sequence points. So you have infinitely many things inside a finitely many things. What can you use? Yes, only one ball must have infinitely many things. What is that thing? No, I mean, what is that principle? Yes, pigeonhole principle. So by pigeonhole principle, at least one of these balls must contain infinitely many. So must contain and subsequence. Okay, of xn1, say. So we denote this subsequence by Sn2. Make sense? Okay. So what's the thing I can do next? I consider smaller ball. Okay, smaller ball. Ball of radius half. And then I also can see the subsequence of who? I don't want to look at the first one already. I want to go smaller and smaller and smaller. So I want to consider subsequence of Sn2. So what we can do is we can define. So first of all, we have xn, x11, x21, x31, okay? And we consider ball of radius 1. There's one infinite subsequence from the first one. We call it x12, x22, x23, x23, so on, right? And then we can keep continue ball with radius 1/3. Okay, we consider subsequence of this Sn2. Okay. So this is the third time we do it. Iterate the third time. But what's the good thing here? The good thing here is we want to define so we can keep doing it. We can define the diagonal sequence. Okay, how do we pick this diagonal sequence? It's a bit like the Cantor diagonalization construction. So we simply pick yi to be yi equals to xii. Okay, so meaning we pick this x11, x1, x22, x33. But what's the thing? What's the good thing about this point? What's the good thing about this point? I want to claim that yi is a Cauchy sequence. Is it Cauchy or not? Why is it Cauchy? If you want to prove it is Cauchy, right? So what's the distance between y, let's say yj and yk? Let's say for j, let's say for j k greater or equals to 2n, let's say. Should be. Not quite right. Not quite right. Should be, let's see. So if I let jk greater or equals to 2n, my claim is this yj and yk should leave. So how do I pick this 2n? Actually, I haven't tell you, right? So this thing here should live inside the ball of 1/2n of y for some y. Is this possible? If this is possible, then I can make sure this is less than 1/n. Is this possible? Is this possible or not? How is it possible?
Sequence of sequence, the n sequence.
Sure. Continue. No. Hey, before we talk about these two, the distance between these two, right? I want to say that these 2 points is within 1/2n from some ball, from some center. Okay, is this true first or not? If this is true, then from this center here, I can use triangle inequality so that these two distance is less than 1/n. And then for any epsilon, you can use this 1/n to estimate it. Is it true for the first one? If I can pick j and k far enough, okay, let's say 2n beyond 2n, and I make sure that they are living in the same ball or not? And then this ball is radius 1/2n. Center, I don't really think. Can or not? Think about how we choose yi. how we choose yi? Every yi is radius 1 over I from some center. Okay. So here is like ball. Our first one don't have ball yet. Second one is ball half. Second, third one is a ball of something. Let's say we put, what should we put? Put zi, z1, and then half of, so 1/3 of z2, something like that. Okay. And then what? Image, sorry. But also note that all these points are subsequence coming from the previous one. So all the sequence below are actually coming from the previous one, in particular the first one. Okay. So, can you imagine or not? Okay, go back and imagine. Tomorrow we continue. Okay, go back and imagine, and tomorrow we continue with this part. A 还是 A5啊？哦 A2，要叫 guard 开一下，等一下。